Chapter 14, ANOVA, Section 14.1, ANOVA, Introduction and Overview. The ANOVA technique was invented in the early 20th century by Sir Ronald Fisher, the same guy as the Fisher transform and like a billion other important things in statistics. I guess statistics books were pretty short before Fisher came around. ANOVA is an acronym for Analysis of Variance. The idea of an ANOVA is to quantify the total amount of variability in a data set, determine how much of that variability is attributable to the independent variables versus how much variability is attributable to noise or other non-measured factors, and then compute the ratio of explained to unexplained variability. If that ratio is sufficiently large, then we consider the IVs to explain a statistically significant amount of variability in the data. There are, of course, many mathematical, implementational, and interpretational details and subtleties that you'll learn in this chapter, but the key concept to keep in mind is that an ANOVA is based on a ratio between explained variability to unexplained variability. Section 14.1.1, When to use an ANOVA. The goal of an ANOVA is to determine the effects of categorical independent variables on a numerical dependent variable. That's the first important thing to know about ANOVAs. They are designed for categorical IVs. If your IV is numerical, so interval, ratio, or discrete, then you would need to discretize the IVs into a relatively small number of bins to use an ANOVA. Although if you have numerical IVs, then the appropriate analysis is regression. Furthermore, ANOVAs are designed for multiple factors or multiple conditions. If you have only two conditions to compare, use a t-test. Here are three examples of experiment designs for which an ANOVA is appropriate. Example 1. Effects of medication type, so red pill, blue pill, placebo, and age group, so young, middle age, and old, on disease severity reduction rated on a 1 to 10 scale. In this case, there are two discrete factors, medication type and age group, and a numerical DV. Example 2, influence of diet, vegan, vegetarian, omnivorous, on body mass index. Here there is one discrete factor, and the DV is numerical. Example 3, effects of educational method, traditional classroom, online learning, blended learning, and grade level, elementary school, middle school, high school, on students' grades. In this design, the two discrete factors are the educational method and grade level, and the numerical DV is the student's performance. And now for contrast, here are three examples of experiment designs for which an ANOVA is inappropriate. Example 1. Test whether people with more Facebook friends have higher self-reported extroversion. Both the IV and the DV are numerical, Facebook friend count is discrete, and extroversion is interval. A correlation analysis or simple regression is appropriate for this design. Example 2. Test whether exam performance can be predicted from the number of hours spent studying and the number of hours spent sleeping. Both IVs are numerical, so a regression is appropriate for this analysis. Example 3. Test whether repetitive stress injury is decreased for a group of meditators versus non-meditators. On the one hand, the IV is discrete and the DV is continuous, so it seems like an ANOVA would be appropriate. However, ANOVAs are suitable for multiple factors or more than two levels within one factor. This example has only one factor with two levels. Therefore, the appropriate analysis is a t-test. In fact, an ANOVA with only 2 groups gives the same results as a t-test. Margin note. Perhaps the label inappropriate is too harsh for this example. Using an ANOVA to compare 2 samples is like hiring a limousine when all you need is a bike. Section 14.2, ANOVA terminology. ANOVAs are chock full of terms that you need to know. These terms will help you understand and apply ANOVAs, will help you talk about ANOVAs to your statistics knowledgeable friends, and will help you seduce that special someone you've always liked who you're convinced would fall in love with you if only you could engage them in a detailed conversation about the mathematics of ANOVAs. Following is a list to get you started. I will introduce a few other terms later in this chapter. Factors. Factors refer to the independent variables in your study. They could be IVs that you manipulate, like music volume, advertisement type, or medication dose. Or they could be naturally occurring, like gender, age group, or country. Levels. Levels are distinct categories or groups within each factor. For instance, a factor, diet type, could have vegan, vegetarian, and omnivorous as its levels. In different scientific contexts, levels might be called conditions, treatments, trials, sessions, or groups. Ways. Ways refers to the number of factors in an ANOVA. A one-way ANOVA has 1 factor, a two-way ANOVA has 2 factors, and so on. The term multi-way ANOVA is a generic term for an ANOVA with more than 1 factor. The number of ways does not determine the number of levels in each factor. In other words, way means the same thing as factor. Footnote. Why does the redundant term way exist? Why not just refer to a 2-factor ANOVA? That is a good question, and I cannot answer it. Back to the text. Subject. A subject provides data. In the context of medical research, the subjects are patients. In psychology research, the subjects are human research participants. In online marketing research, the subjects might be websites. In cosmological research, the subjects are stars, and so on. More generally, the subject is the person or object that provides a unit of data. Repeated measures. In a repeated measures design, the same subjects are measured under different conditions or over multiple time points. That is, each subject provides data for each level of 1 or more factors. This is often the case in studies involving interventions, so medical treatments or different conditions within an experiment, or changes over time. Repeated measures are also called within subjects or dependent samples. Between subjects. In a between subjects ANOVA, each subject is measured only on 1 level of 1 factor. For example, a study on education in which each student experiences only 1 of 3 teaching methods would be analyzed using a between subjects ANOVA. This is also sometimes called an independent samples ANOVA. A multi-way ANOVA that has both repeated measures and between subjects factors is called a mixed effects ANOVA. An example of a mixed effects ANOVA is if 3 groups of students are randomly assigned to different teaching methods, that's the between subjects factor, and are tested at the start and at the end of the academic year. That's the within subjects factor. Main effects and interactions. These terms are used in a multi-way ANOVA. A main effect is the impact of 1 factor on the DV averaging across, that is, ignoring the levels of the other factors. An interaction effect is when the impact of 1 factor depends on the level of another factor. As an example, consider a study on the effects of diet, so low sugar or high sugar, and exercise, so none versus regular, on weight loss. A main effect of diet could be that people lost weight on a low sugar diet regardless of whether they exercised. An interaction could be that people on a low sugar diet lost weight only if they exercised regularly. Balanced versus unbalanced. A balanced design is when there is an equal number of observations in each level of a factor. An unbalanced design is when the number of observations varies between levels. Experiments can become unbalanced during data collection or when removing outliers. Sample size imbalances do not change the validity or the interpretation of the ANOVA, although the underlying equations become more complicated. Extreme imbalances can reduce the accuracy of model estimation. Fixed versus random effects. Fixed effects are factors within levels that are specifically chosen by the researcher, for example, certain age groups, whereas random effects are factors within levels that are randomly sampled from a larger population, for example, randomly chosen schools from across the country. Here's an example. A factor home type is a fixed effect with levels dorm room, apartment, and house. And a factor nurse is a random effect because we select nurses at random to determine if patients' hospital duration depends on the individual nurse. Factor nurse could be transformed into a fixed effect if we group nurses by age group or gender. MANOVA, multivariate analysis of variance, is an extension of ANOVA when there are multiple dependent variables to be considered. ANCOVA, analysis of covariance, is an extension of ANOVA that includes additional continuous variables, so covariates, to control for their effect, which is then used to remove the impact of confounding variables. Margin note: I do not discuss MANOVAs or ANCOVAs in this chapter. However, these advanced extensions of ANOVA are based on the same math as the quote-unquote regular ANOVAs, so completing this chapter will put you in a great position to understand advanced ANOVA topics. Section 14.2.1 Factorial Design Table. A factorial design table is a way to organize your experiment design and sample sizes into a table. This table is useful because it will help you, number one, design the experiment before collecting the data, number two, understand how to set up the ANOVA, and number three, interpret the results of the ANOVA. Figure 14.1 shows a factorial design table. The numbers reflect the sample size per cell, and the total, row and column, so the rows and columns labeled total, show the marginal sample sizes. This is an unbalanced design because the number of participants is different in each cell. There were 125 participants in this study, and, for example, 19 of them were old and took the blue pill. There are two factors: medication with 3 levels and age group with 2 levels. Such a design is referred to as a 2x3 ANOVA. This paragraph refers to figure 14.1, which shows a factorial design table for a 2x3 ANOVA. Here we see a table with the title on top of the columns as medication, that's one factor, and the title of the rows is age group, that is the other factor. Now, factor medication has 3 columns corresponding to 3 levels within this factor, and they are labeled blue pill, red pill, and placebo. And then the age group factor has 2 levels, young and old. These correspond to 2 rows. So there are numbers between 19 and 21, 22, within each of the cells in this 2x3 table of numbers, and those numbers correspond to the sample sizes within each of those cells. So for example, there were 19 samples in old people who took the blue pill. And then we see all the way to the rightmost column and the bottommost row is the total sample size. So that is the sample size for all of the young people. And for example, down each column would be for all the people who took the blue pill, all the people who took the red pill, and so on. Back to the text. Factorial design tables can also display cell means or other characteristics. If the numbers reflect the cell means, the total, row and column, would show the marginal means, which are the averages of each level, ignoring the other level. If the design is balanced, then the marginal means equal the means of the cells, but in an unbalanced design, the cell means are sums averaging over a different number of samples, in which case the marginal means might be different from the means of the samples. A comment on sample sizes. ANOVAs do not need to have equal sample sizes in each cell unless the factor is a repeated measure, in which case an unbalanced design indicates missing data. You'll see in the math that the variability across cells is scaled by the sample size within each cell. So why do people often recommend striving for a balanced ANOVA table? The thing is that having equal sample sizes is not so important per se. Having comparable variances across cells is important. In fact, it's one of the assumptions discussed in the next section. Having equal sample sizes helps to ensure, though does not guarantee, that the samples are good estimates of the population, variances, and means. Minor differences in sample sizes across cells, for example, n equals 78 in one cell and n equals 81 in another cell, is not something to lose sleep over. But large differences in sample size, especially if some sample sizes are small, for example, n equals 5 in one cell and 200 in another cell, this is a cause for concern. It's not a math problem. The ANOVA calculations work equally well with n equals 5 as with n equals 5,000. The problem is that small sample sizes increase the risk of statistical errors. Relation to ANOVA table. You might be tempted to call the factorial design table an ANOVA table. That's an understandable temptation because it is a table that you use for an ANOVA. However, the term ANOVA table is reserved for a collection of numerical values that result from calculating the ANOVA on the data. You'll learn about that later in this chapter. Section 14.2.2, Assumptions of ANOVA. By this point in the book, you are used to the idea that all statistical analyses have assumptions. ANOVAs are no different. The following list introduces the assumptions of ANOVAs. Throughout the rest of this chapter, I will show you how to evaluate qualitatively and quantitatively whether your data conform to these assumptions. Independence. Each data point should be independent from all others. You can ensure that this assumption is met by obtaining a sample that is random and representative of the population to which you wish to generalize. This assumption can also be violated if you are running ANOVAs on time series or image data, in which case neighboring time points are likely to be correlated. Normality. The residuals, the difference between the observed and model predicted values, should follow a normal distribution. Normality of residuals can be checked graphically using a QQ plot and statistically using normality tests such as the Shapiro-Wilk test. Homogeneity of variance, also called homoscedasticity. The variability should be comparable across all levels of the independent variables. This is also known as the assumption of equal variances. It can be checked visually by plotting the residuals versus fitted values or statistically using Levene's test. No multicollinearity. Multicollinearity is a fancy term for redundancies in the IVs. Multicollinearity is usually more of a concern for multiple regression than for ANOVA, but multicollinearity can prevent the variance from being correctly calculated in the ANOVA table. No outliers. All parametric statistical analyses are sensitive to outliers. ANOVAs are particularly sensitive to outliers because they are based on squared terms. Large outliers or multiple outliers in one condition can make the ANOVA results unreliable. Outliers can be particularly detrimental in small samples. ANOVAs tend to be robust to minor violations of these assumptions, especially if the sample size is reasonable. Now, I realize that previous sentence is vague. How robust are they? How minor are the violations? And what is a reasonable sample size? It is difficult to be precise about claims like this because the robustness of statistical analyses to violations of assumptions depends on the data and the effect sizes. Later in this chapter, you will learn how to inspect the ANOVA results, mainly the residuals plots, for strong violations. I also believe that simulated data can help you build intuition for the robustness of ANOVAs, and you'll explore this in several of the exercises. Section 14.3, the math of the ANOVA. Remarkably, all of the math underlying ANOVAs comprises addition, subtraction, exponentiation, and division. Therefore, if you survived middle school math, you can understand ANOVA math. You learned above that there are several flavors of an ANOVA. So one-way versus multi-way, balanced versus unbalanced, fixed versus random versus repeated effects, and so on. In this section, I will describe the math of the one-way between subjects ANOVA. It's the simplest ANOVA flavor and therefore a good way to approach the math. More complicated ANOVAs have more complicated math, but the concepts are the same. Section 14.3.1, the ANOVA model. All statistical analyses are based on crafting a model of the data and then testing whether that model is a good fit to the data. In an ANOVA, the prediction for each observation is simply the mean of the group to which it belongs. Thus, we can construct a model equation that includes a term for the level, so the predicted value, and a term for the residual, the unexplained variability. In the equations below, x hat sub ij is the predicted data value for subject I in level j. Here we have two equations. Equation 14.1 reads x hat sub ij equals x bar sub j. And the next equation, equation 14.2, reads x sub ij equals x hat sub ij plus epsilon sub ij. Back to the text. The idea is that the ANOVA makes a prediction about a data value, which is that the data value exactly equals the mean of the group. There is no subject level predictor, that is no sub-I term in the right-hand side of equation 14.1, which means that the ANOVA model assumes that individual variability is error. In reality, data are never perfectly predicted by the model, and the difference between the measured data value, so that's x sub ij, and the predicted data value, that is x hat sub ij, is epsilon sub ij, which is called the error or residual. I'm being conservative in those equations. You could write equation 14.1 as x hat sub ij equals mu sub j, indicating that the predicted data value is the population mean of condition j. Using x bar sub j assumes that the sample condition mean is a good estimate of the population mean. If the ANOVA is a good model of the data, then the epsilon sub ij terms should be small. They should also have a normal distribution and be of comparable magnitude for all levels in all factors. If there are systematic deviations of the residuals across conditions, then the data violate an ANOVA assumption. Section 14.3.2 ANOVA hypotheses. Of course, the hypotheses you specify are unique to your experiment design and research questions, but the ANOVA itself tests against the same null hypothesis regardless of the details of the design. Here we have two equations, equation 14.3 and equation 14.4. For equation 14.3 reads H naught is mu sub 1 equals mu sub 2 equals ... equals mu sub k. And HA is mu sub j is not equal to mu sub m. Back to the text. In words, the null hypothesis of an ANOVA is that the means of all cells for all factors and all levels are equal. So K indicates the total number of cells in the factorial design table, and J and M are any two conditions. The alternative hypothesis is that at least one cell is different from at least one other cell. Philosophical side note. Why did I use x bar sub j for the model, but mu sub j for the hypotheses? The sample mean is a descriptive statistic, so the hypothesis that x bar sub j equals x bar sub m is trivially disproven when, for example, x bar sub j equals 4, while x bar sub m equals 4.000001. But from an inferential statistical perspective, we don't care about x bar sub j. Instead, we use the sample mean to estimate an unknown population mean, mu sub j. X bar sub j not equal to x bar sub m does not imply that mu sub j not equal to mu sub m due to sampling variability. Importantly, the alternative hypothesis does not specify which cells differ. For example, if k equals 3 and the ANOVA is significant, then we would not immediately know which cells are different from which other cells. All we would know is that the mean of at least one cell is significantly different from the mean of at least one other cell. To determine which conditions provided sufficient evidence to reject H0, you would need to visualize the data and perform additional tests. I'll get back to this test later in the chapter. First, you need to learn the math underlying ANOVAs. Section 14.3.3 Sum of Squares. Each statistical analysis has one computation at its heart. With the t-test, that is an average scaled by the standard error of the mean. With correlation, that is a dot product scaled by variances. The one computation at the heart of the ANOVA is called the sum of squares. Here's the general formula for the sum of squares. Equation 14.5 reads, SS stands for the sum of squares, equals the sum from I equals 1 to n of the quantity x sub I minus x bar, that quantity squared. Back to the text. Does that equation look kind of familiar? I sure hope so. In fact, the sum of squares is nearly identical to the formula for variance. The only difference is that variance involves dividing by n minus 1, whereas the sum of squares does not. This has several implications. Implication 1. Sum of squares has the same interpretation as variance. the amount of spread of the data around the mean. Implication 2. Sum of squares trivially increases with sample size. This is a limitation of interpreting the sum of squares on its own, but you'll see later that we scale the sum of squares when computing the statistical values. Implication 3. The squaring makes sum of squares sensitive to large outliers, which is an important consideration when applying ANOVAs to data that contain excessive noise or outliers. How is the sum of squares used in an ANOVA? The idea of an ANOVA is to represent the total variation in the data set as the sum of the variation resulting from the experiment design plus variation not attributable to the experiment design. Conceptually, you can think of the total variation in the data as represented by a pie chart, divided into two slices, the variation that is explainable by the IVs and the rest of the variation. Unexplained variation is not necessarily random noise. It can include meaningful variability, but that variability is unrelated to the IVs. This paragraph refers to figure 14.2, which shows the conceptual idea of statistical significance of an ANOVA. So we have the total variation separated into what can be explained and what cannot be explained by the IVs. Here we see a fraction of F equals explained variability, the words explained variability divided by unexplained variability. And below that simple equation, we have two pie charts. On the left, the pie chart is mostly light gray with a small piece for dark gray. Again, the light gray corresponds to the variation that can be explained by the IVs, and the dark gray corresponds to variation that cannot be explained by the IVs. The text inside the pie says ANOVA is significant. To the right of that, we see another pie, which is kind of the reverse. So most of the pie is in dark gray. And again, that corresponds to variation that cannot be explained by the IVs, and a relatively small proportion of the pie is light gray. And here the text reads, ANOVA is non-significant. Back to the text. Section 14.3.4, ANOVA as a partition of variability. I hope that you find figure 14.2 conceptually comprehensible. The purpose of this subsection is to make that concept concrete. There are three SS terms that underlie the one-way ANOVA. The SS total is all variability in the dataset, which is like the entire pie in figure 14.2. SS total can be decomposed perfectly into the sum of the SS between and SS within. Between is short for the variability between the levels of a factor, and within is short for the variability within each level. So the light gray part of the pie that I described in figure 14.2 represents SS between, and the dark gray piece of the pie represents SS within. Here is the math. Below we have a series of three equations. The first equation is for SS total. That equals a double summation, and inside the actual term that's being summed over is x sub ij minus x bar, that difference squared, and then we sum over all of the individuals within each level and then over all of the levels. So essentially, we are computing the difference between the grand mean, the mean of the entire data set, versus each individual data point across all of the levels within the factor. Then we have df total equals n minus 1. So the degrees of freedom for SS total is n minus 1. That's equation 14.6. Equation 14.7 is also a summation, but it's only one summation. And this summation is over the levels. This is for SS between. So we are summing over the levels of x bar sub j minus x bar, that difference squared, times n sub j, where j corresponds to the particular level within each factor, so the number of observations within each factor, and x bar sub j is the mean of level j. And here we have df for between is k minus 1. Again, k is the number of levels. The third equation is 14.8, and that's the equation for SS within. And here, again, we have a double summation sign over the subjects or observations within each level, and then the total number of levels. And the term inside the double summation is x sub ij, so each individual data point, minus x bar sub j, and that quantity squared. And the degrees of freedom for the SS within is n minus k. Back to the text. K is the number of levels within the factor, n is the total number of subjects, and n sub j is the number of subjects in each level. In a balanced design, all of the n's are equal, but these numbers can differ in an unbalanced design. This scaling term is necessary because the other SS terms grow larger with sample size, and so the n sub j allows the SS between term also to increase with sample size. Now, x bar is the grand average. That is the average of the entire data set pulling over all ANOVA cells. In contrast, x bar sub j is the average within level j. Thus, for example, an ANOVA design with one factor and 3 levels would have one value of x bar and 3 values of x bar sub j. A few comments and interpretations. Comment 1. The SS total is the total variability in the entire dataset, ignoring the experiment design. I wrote that equation with 2 summation terms, but if the design is balanced, the equation can be simplified to 1 summation over n observations instead of n sub j observations per level. Comment 2. The SS between is the variability across levels. There is no index I in this equation, which means that individual variability is ignored. SS between assumes that all individuals within a cell are describable only using their cell mean. Consider how this relates to the ANOVA model equations presented earlier. Comment 3. The 3 SS terms are closely related. SS total equals SS between plus SS within. In other words, the total amount of variability in the data is the sum of the variability between levels plus the variability within levels. However, the F ratio is not defined as SS between divided by SS within for reasons I will explain in the next section. Comment 4. Linking back to figure 14.2, the explained variability is SS between scaled by its df, and the unexplained variability is SS within scaled by its df. Comment 5. You will see different terms for these cells. What I call between is also called treatment, condition, or group. Similarly, what I call within is also called error or residual. Footnote. I dislike calling it quote-unquote error. Although some variability within a group does reflect errors, it also includes experimental, genetic, psychological, cultural, and other meaningful individual differences that are not modeled in the ANOVA. End of footnote. On behalf of statisticians everywhere, I sincerely apologize for any confusion this may cause. If World War III could be averted by having all scientists agree on one set of terminologies that everyone uses, then we're doomed. The silver lining of inconsistent terminology is that it forces you to understand concepts instead of memorizing formulas. Equation 14.3.5, mean square and the F statistic. To counteract the trivial growth of SS with increasing sample size, the SS is divided by the degrees of freedom. That gives us the mean squared variability, commonly abbreviated MS. Here we have two equations. Equation 14.9 reads MS between equals SS between divided by DF between, and equation 14.10 reads MS within equals SS within divided by DF within. And this brings us to the formula for the F statistic. Equation 14.11 reads F with two numbers in the subscripts k-1 and n-k equals MS between divided by MS within. Back to the text. The F statistic has a pair of degrees of freedom. They are called the numerator, that's k-1, and denominator, that's n-k, degrees of freedom. Together, these parameters control the shape of the H0 F distribution, which you'll see in a few pages. Mathematically, these two DF values can be any positive numbers. However, in the context of an ANOVA, the numerator degrees of freedom will be smaller than the denominator degrees of freedom because there tends to be many observations compared to experiment conditions. Thus, n is greater than k. A larger denominator degrees of freedom compared to the numerator degrees of freedom can actually happen in a multifactorial design with relatively few observations. There's nothing intrinsically wrong with that, but it could indicate that the sample size is too small for the experiment design. Perhaps you are confused by the pie charts in figure 14.2 by thinking that the F ratio would be the ratio SS between divided by SS within. This is an incorrect formulation because increasing the number of subjects or the number of conditions would speciously inflate the F value, just like increasing the number of data points would inflate the standard deviation without dividing by n-1. In other words, the SS quantities need to be appropriately normalized by their respective degrees of freedom before they can be compared. Interpreting the F ratio. The F ratio is variously called the F value, F score, or F statistic. It is the ratio of the estimates of the population variance between groups versus the variance within groups. The MS between is the variability across the means of the groups, thus ignoring individual variability within each group, while the MS within is the variability within the groups, ignoring variability across the groups. There are no subtractions or specific comparisons across groups, which is why the F-test provides no information about which conditions have different means. It simply indicates the variability across groups relative to the variability within groups. As a ratio, we can consider different ranges of F. In particular, F less than 1. The dispersion within each group is larger than the dispersion between the group means. This result leads to a failure to reject the null hypothesis, implying that there are no significant differences among the group means. F equals 1. The variability between group means is equal to the variability within groups. This could occur when the group means are close to each other, again suggesting that there are no significant differences among the group means. F greater than 1. The dispersion across group means is greater than the average dispersion within the groups. A sufficiently large F value indicates that there is a significant difference among the group means. F less than 0. The F statistic is a ratio of two positive quantities and therefore cannot be negative. If you get a negative F value, then something went horribly wrong somewhere. As I wrote earlier, the exact critical value of F corresponding to P less than 0.05 depends on the degrees of freedom, but in many experiments, it's in the range of 2 to 5. You can directly interpret this number. For example, an F ratio of 4 means that there is 4 times as much variability across groups than within groups. P-values. Obtaining a p-value from an F-value is conceptually the same as obtaining a p-value from a t-value. It is simply the sum of the probabilities to the right of the observed F-value. And the interpretation is the same. The p-value is the probability of obtaining a test statistic larger than the observed value under the assumption that the null hypothesis is true. Because f-values are non-negative, all f-tests are one-tailed. Figure 14.4 shows a few f distributions for selected df pairs along with their critical f values. This paragraph refers to figure 14.4, which shows f PDFs for a selection of df pairs. The critical f values corresponding to p less than 0.05 are indicated with downward-facing arrows. So here we have a line plot with f value on the x-axis ranging from 0 to 3.5, and the probability density on the y-axis. And then we have 5 lines that are drawn in different shades of gray. And these lines all look roughly similar, except for one line, which doesn't actually have it doesn't go down to 0 at the left side as f approaches 0. But the other 4 all look fairly similar in terms of the shape of the distribution. They do not look Gaussian because they are skewed to the right. They all start at 0, a probability of 0 for f equals 0 because f values cannot be negative. And they peak at somewhere around 0.5 to 0.7, and then they slowly decay as the f value increases. So then we see the downward arrows to the right indicating the critical values of f for different degrees of freedom pairs. So these would be the values of f that would give a p-value of 0.05. And they vary depending on the degrees of freedom, but the smallest critical f value that's illustrated in this plot is 2.42, and the largest is 3.32. Section 14.4, the ANOVA table. The formulas I described so far are organized into the ANOVA table. Figure 14.5 contains no information that I haven't already presented, but please inspect it carefully to make sure you understand each cell. Figure 14.5 shows an example of a one-way ANOVA table. There are 3 rows and 4 columns. The first row is labeled between, the second row within, and the third row is labeled total. And then we have the columns for SS, DF, MS, mean square, and the final column is labeled F. Now, inside the SS columns are the equations that I described earlier for computing the sum of squares for between, the sum of squares within, and the sum of squares total. Then we have the degrees of freedom, also as I have described earlier, and then the mean square, as I have described earlier as well. And then we have the final column and the first row, that is the F value, and that is the ratio of MS between to MS within. A few comments about this table. Comment 1. Notice that the only F value, and therefore the only p-value, is associated with the between groups row. There is no statistical test associated with the within groups variance. That's just used as the denominator because it reflects the variance that cannot be attributed to the experiment design. Comment 2. The total variability is not used in the ANOVA calculation. In fact, the SS total row does not need to be included in the table and is sometimes omitted. However, you can use the SS total line as a sanity check to confirm that SS total equals SS between plus SS within. Comment 3. Remember that a significant F statistic doesn't tell you which conditions differ. It merely indicates that the average of at least one cell is significantly different from the average of at least one other cell. For this reason, the F statistic is sometimes called an omnibus F-test. You'd need to visualize and do post-hoc testing to determine which conditions differ. More on this later. Comment 4. The ANOVA only tests for differences in means. It is possible that different levels have similar means but different standard deviations or skew or correlation with some other variable or any other statistic. If you have an a priori hypothesis about group differences in a descriptive statistic other than the mean, then ANOVA is not the appropriate analysis method. Comment 5. A one-way ANOVA with two levels is the same thing as a t-test. In this case, the F statistic is the squared t statistic with the same degrees of freedom. You'll confirm this in exercise 3. Comment 6. Multi-way ANOVAs have an SS between term for each factor, and therefore the ANOVA table has more rows, and even more rows for interaction terms. I'll get back to this later in the chapter. Final comment for this section. Why do we focus on the sum of squares, and why do we call it mean squares instead of variance? Wouldn't it be simpler to explain the math if we just completely dropped the SS and called MS variance? Also, considering we call it an ANOVA and not ANOS for analysis of sum of squares, or ANOMS for analysis of mean squares. Well, first of all, I did not invent this analysis, so don't be angry with me. More importantly, there is a good reason to conceptualize ANOVAs in terms of the sum of squares. This is what allows us to partition the total variability in the data into different compartments. That is, the sum of squares total equals the sum of squares between plus the sum of squares within, but the mean squared total does not equal the mean square between plus the mean square within. In other words, the sum of squares terms have a perfect relationship, while the mean square terms do not. As for why we don't call MS variance, technically those are different quantities. For example, because of the n sub j term in the MS between. Although they are conceptually comparable. Now, none of this explains why we call it ANOVA instead of ANOMS. Maybe it would be internally consistent to call it analysis of variabilities. Anyway, that's enough ranting. Section 14.5, Post-hoc comparisons. Imagine a one-way ANOVA with 4 levels and a statistically significant F-score. As you now know, the significant F does not tell you which of the 4 conditions actually differ, and yet the purpose of the research is likely to determine which conditions differ. I'm sure you agree that that's an annoying situation. We want to know what is different, not only that something, somehow is different. We can start to gain insight by visualizing the data. Figure 14.6 shows a possible outcome of the analysis. This paragraph refers to Figure 14.6, which illustrates condition averages from a one-way ANOVA with 4 levels. We have a bar plot with the y-axis labeled outcome variable and the x-axis labeled condition or level with 4 tick marks indicating conditions A, B, C, and D. And what we see visually is that A and B have basically the same numerical value on the y-axis. C is much higher than A and B, and D is a little bit higher than C. Back to the text. It looks like conditions A and B are different from conditions C and D. Is it appropriate to test all possible comparisons using t-tests? With 4 conditions, there are 6 possible comparisons, so if you were to perform all possible t-tests with an alpha threshold of 0.05 per test, the family-wise error rate could be as high as 0.3. That is unacceptably high. Applying Bonferroni correction to evaluate each individual test at 0.05 divided by 6 would give a test-wise alpha of 0.0083, but that is very stringent and even true effects might not reach significance. Furthermore, given that all these tests come from the same ANOVA, it is unlikely that they meet the independence assumption of Bonferroni correction. But there is a larger issue here, which is that the denominator of the t-test is inappropriate. Here's why. In an ANOVA, the denominator of the F statistic is MS within, which is an estimate of the within-group variability across all groups. This is based on the assumption that the variances of the sampled populations are equal. Adapting the denominator to each comparison pair violates this assumption. The solution is to apply a post-hoc comparison. This term refers to tests of specific contrasts like A versus C in the context of an ANOVA. Post-hoc comparisons are conceptually similar to t-tests, but are modified to appropriately incorporate ANOVA variability. There are several post-hoc comparisons methods. Below, I will introduce you to 3 of them, with the most detail on the Tukey test. Section 14.5.1, Pass the Tukey. The Tukey test for post-hoc comparisons is designed to control for the family-wise error rate. It's called the Tukey Honest Significant Difference, abbreviated HSD, and its statistical value is called Q. Q is conceptually similar to a t-test, but behaves like an F value. Here's the formula. Equation 14.12 reads Q sub ij equals the fraction with the numerator x bar sub I minus j bar sub I, and the denominator is the square root of the summation of ms within divided by n sub I plus ms within divided by n sub j. Back to the text, where x bar sub I is the average of group I and n sub I is the sample size of group I. The denominator simplifies a bit in a balanced ANOVA. The numerator is set up such that x bar I is greater than x bar sub j. This is because the distribution of H0 Q values is positive, so Q must be a positive number. Q takes 2 degrees of freedom, K and N minus K. In other words, we have Q, parenthesis, K, comma, N minus K, N parenthesis. K is the total number of groups in the ANOVA, so the total number of cells in the Factorial design matrix, and N is the total sample size. This is not the same as the sample size of the 2 comparison groups. A p-value is computed from the Q value. The Q values are distributed according to a studentized range distribution. The scipy.stats library in Python has a function called studentized range that computes this distribution, and you can see some examples in figure 14.7. However, in practice, you would usually call a function, for example, in stats model in Python or the Tukey HSD function in R, to implement the Tukey test. I'll show you how to do that later in this chapter. This paragraph refers to figure 14.7, which shows studentized range distributions for various values of Q, using the same degrees of freedom parameters that were used to illustrate the F distributions in figure 14.4. That was the figure that illustrates various F distributions for different degrees of freedom parameters. In the plot itself, we see a line plot with 5 lines, and the x-axis is Q, ranges from 0 to 6. The y-axis is the probability density. We see that most of these curves look somewhat like an F distribution, kind of a little bit Gaussian or x-Gaussian, although they taper to 0 on the probability y-axis at x equals 0 or q equals 0. And these ones that I'm showing here peak at roughly around 2 to 2.5, and they slowly taper down to 0 as we get to 6, a q value of 6 and above. Back to the text. Q looks like a combination of a t-test and an f-test. Its numerator is the same as that of a t-value, and its denominator is a measure of standard error, but the error term comes from all groups, including the groups that are not included in the numerator. The degrees of freedom are nearly identical to those of the F statistic. We have F with k minus 1 and n minus k degrees of freedom, but Q with k and n minus k degrees of freedom. Why does Q not have the minus 1? With the Tukey post-hoc test, we don't mean center the individual comparisons, so we don't trivially know the jth cell mean simply by knowing the ith cell mean. Therefore, the degrees of freedom is k. Scheff's test. Scheff's test is used to evaluate all possible comparisons, not just pairwise comparisons, but also comparisons of groups of means. For example, comparing whether levels A and B collectively differ from level C. This is a distinguishing feature compared to the Tukey test, which is designed to compare pairs of means. Scheff's test is more conservative, meaning that the Tukey test is more sensitive to detecting potentially small effects. If you have specific hypotheses, use the Tukey test. If you want to throw everything against the wall and see what sticks, Scheff's test is better controlling for type 1 errors. Dunnett's test. Dunnett's test is used to compare k-1 group means with one selected group. This is appropriate for experimental designs where multiple treatment groups are compared to a single control group. For example, imagine a medical study in which 4 different medications are tested against a placebo. Dunnett's test would be used to compare each of 4 medication groups against the placebo group. This is a non-exhaustive list of post-hoc methods for an ANOVA, and I do not wish to imply that any method not discussed here is inappropriate. All post-hoc tests have in common that they incorporate variance estimates and degrees of freedom parameters that reflect the entire ANOVA table and not only a pair of samples. Specific post-hoc tests are customized for specific purposes. Section 14.5.3, When and What to Test. Only with a significant F. Post-hoc comparisons can be done only if the F statistic is statistically significant. It is not appropriate to perform t-tests on pairs of levels within a factor without the omnibus F having p less than 0.05. Indeed, a non-significant F value indicates that the means are not different. Therefore, if a 2-sample t-test of groups inside an ANOVA has p less than 0.05 while the F value is p greater than 0.05, then either the t-test is a type 1 error or the variances are so different across levels that the data violate an ANOVA assumption. Keep it simple. Here's some advice. Don't test more comparisons than are helpful for interpreting the ANOVA. There is a difference between being able to control for multiple comparisons versus being able to interpret a myriad of comparisons. When you have a significant F-test, inspect a bar plot of the data and use your expert domain knowledge to determine which groups make sense to compare. To be clear, I am not suggesting to avoid comparing groups. However, it is important to be aware that each additional comparison increases the potential for interpretational confusion and complication. This isn't a major concern for one-way ANOVA, but the complexity increases quickly. For example, a 3x4x5 ANOVA has 19 possible pairwise comparisons. Section 14.6, Effect Size. One of the amazing things about the ANOVA is that because it is based on quantifying and partitioning variability, it is straightforward to quantify the proportion of variance that is attributable to the factors. In particular, we can quantify the effect size to understand how important an experimental variable is. Importance, quote unquote, is defined as the amount of variability explained by a factor. Think back to the conceptual pie charts in figure 14.13. Consider that if all the variability in the data were explained by the model, then the entire pie would be light gray, so that is the SS between. Conversely, if none of the variability were explained by the model, then the entire pie would be dark gray. That corresponds to the sum of squares within. That is the intuition behind eta squared, and I'm pretty sure you would come up with this formula on your own. Here we have equation 14.13, which reads eta squared equals the fraction of sum of squared between divided by sum of squared total. You can see from the formula that eta squared is the fraction of the total variability that is attributable to the factor. It's called eta squared because the SS terms are squared. Note that this is not the same thing as the F ratio because the F ratio is derived from the mean squared terms and the two mean squared terms do not sum to the total variability. There are no specific values of eta squared that are universally considered sufficient. In the social sciences literature, eta squared between 0.01 and 0.06 is considered small. Eta squared between 0.06 and 0.14 is considered medium, and eta squared larger than 0.14 is considered large. But those are rough guidelines, even more arbitrary than the p-value threshold of 0.05. Because eta squared is a proportion of variabilities, an appropriate interpretation, for example, of eta squared equals 0.18, is 18% of the total variability in the dependent variable is accounted for by the independent variable. R squared. R squared is a measure of effect size that appears in many analyses. You've already seen it in chapter 11 in the t-test, and you'll see it again in the next chapter on regression. Here's the formula for R squared in the context of ANOVA. Here we have equation 14.14, which reads R squared equals the fraction of SS between over SS total. Hey wait, isn't that identical to eta squared? Yes, it is. For a one-way ANOVA, R squared equals eta squared. They are not equal for more complicated ANOVA designs. More on this later in the chapter. Section 14.6.1, Less Biased Estimators. Eta squared is a biased estimator. Because eta squared is calculated using data from one sample, it does not account for the variability in estimates that we might expect if we were to take many samples from the population. This means that eta squared is an imperfect estimator of the true effect size, although it is more reliable for larger sample sizes. Furthermore, eta squared tends to overestimate the effect size, in part because the errors are squared and therefore always positive. And the squaring means that overestimates are larger than underestimates. And also in part because you are unlikely to look at eta squared unless the F statistic is already significant, which means that eta squared is more likely to be interpreted in samples that, due to random variability or systematic experimental or researcher biases, contain type 1 errors. Actually, this issue of being more likely to interpret type 1 than type 2 errors permeates all of statistics, not only eta squared. There are two less biased effect size estimators that you can use. Footnote: These estimators are better than eta squared, but they are not guaranteed to be completely free of bias. Therefore, they are given epithets like less biased or lower bias instead of unbiased. End footnote. One is called partial eta squared and is used for multi-way ANOVAs. I will define and explain this term later in the chapter. The less biased effect size estimator for a one-way ANOVA is called omega squared and is defined as follows. Here we have equation 14.15, which reads omega squared equals the fraction with the numerator being SS between minus degrees of freedom between times mean square within, and in the denominator we have sum of squares total plus mean squared within. Back to the text. Don't be too intimidated by that equation. The formula for eta squared is embedded in the ratio. Indeed, you can rewrite that equation as follows. Here we have equation 14.16, which reads omega squared equals eta squared times a bunch of stuff that I won't read out, but suffice it to say, the important point of this equation is that we have omega squared equals eta squared times some scaling factor. Back to the text. Don't get too hung up about interpreting equation 14.16. The main point is to appreciate that omega squared is simply eta squared with a scaling factor. Let's go back to thinking about equation 14.15. The numerator can be seen as a corrected estimate of the variability explained by the factor. It takes the explainable variability and subtracts a term that estimates the unexplained variability scaled to the magnitude of SS between. The denominator is the total sum of squares plus the unexplained variability. Eta squared and omega squared become more similar as the sample size increases. This happens because the SS terms grow monotonically with sample size, whereas the MS term does not scale with sample size. Thus, as the sample size increases, omega squared can be approximated as SS between divided by SS total. Adjusted R squared. R squared is biased for the same reason that eta squared is biased. Therefore, an adjusted R squared is used. Here we have equation 14.17, which reads adjusted R squared equals 1 minus the fraction with the numerator being the product of two terms. First term is 1 minus R squared. Second term is n minus 1. And the denominator is n minus k minus 1. Back to the text. In particular, when new predictors are added to the model, the adjusted R squared increases only if the new predictor improves the model more than what would be expected by chance, and it decreases when a predictor improves the model by an amount that could be expected by chance. Section 14.6.2, Effect Size versus P-Value. I've mentioned several times in previous chapters, for example, in the discussion about confidence intervals in section 13.5.1, that p-values are not measures of effect size. Eta squared and p-values are related in that they both provide information about the effect of an independent variable on the dependent variable in a statistical test, but they describe different aspects of the effect. In particular, eta squared quantifies the proportion of the total variability in the dV that can be attributed to the IV. Eta squared helps you understand the practical significance of the effect, but does not provide information about statistical significance. Indeed, there are no probabilities associated with eta squared. Furthermore, the p-value assesses the probability of observing the obtained f-value if the null hypothesis were true. The p-value does not provide information about the magnitude of the effect. Indeed, a p-value can be small even with a tiny effect size. Both quantities are relevant and interpretable, and both should be inspected and reported. As a general guideline, the p-value is relevant for statistical significance, while the eta squared is relevant for practical significance. You'll explore the relationship between these quantities in several of the exercises. Section 14.7 One-Way ANOVA Example. Enough with the abstract equations. Let's work through an example. In this section, I'll show numbers and an ANOVA table without all the tedious intervening arithmetic. Your job in exercise 1 will be to write code that calculates all that tedious arithmetic. Here is the very serious and very scientific research study that I did. I wanted to know whether elves, dwarves, or trolls could cast more spells more quickly. So I went to a magical fairyland on a research trip funded by the European Fake Research Council, found a bunch of these magical creatures, and timed how many spells each one could cast in 60 seconds. Figure 14.8 shows the factorial design table. There was one factor, which is the creature type, 3 levels, and a slightly unbalanced design because I couldn't find as many elves willing to participate. This paragraph refers to figure 14.8, which shows the factorial design table for our magical experiment. This table has 2 columns. The first column is labeled creature, the second column is labeled n, and there are 3 rows corresponding to the elves, which has an n of 13, dwarves with an n of 14, and trolls with an n of 14. And then actually there's a 4th row in there called total, which is 41. Back to the text. Figure 14.9 shows the means and sample sizes, and the text below shows the ANOVA table. Written out in formal statistical language, we would say that the main effect of creature type was statistically significant. F with 2 and 28 degrees of freedom equals 4.51, and the p-value was 0.0174. This paragraph refers to figure 14.9, which shows the mean and sample sizes of spells cast per minute. Error bars indicate standard error of the mean. So we have bar plots with 3 bars for elves, dwarves, and trolls, and the mean of the elves is 17.5, the mean for the dwarves is 16.8, and the mean for the trolls is 13.6. Back to the text. Get in the habit of inspecting an ANOVA table. Here are some observations based on the ANOVA table that you should make. Observation 1. Make sure the degrees of freedom make sense. df between is defined as k-1, and here we have 3 levels. In the ANOVA table, we have the df in the row called between equaling the number 2. So then we have df within is defined as n-k, which makes sense. We have 41 creatures and 3 types of creatures, and the df total is n-1. So looking back to the ANOVA table, we have df of the within row is 38. The df for the total row is 14. Observation 2. Do a quick F calculation. 58 divided by 12 is roughly equal to 5. In the table, we have the mean squared error for the between row is 58.55, and the mean squared error for the within row is 12.97, and the F value for between is 4.51. When you get to multi-way ANOVAs with interaction terms, doing these quick calculations will remind you of where each F value comes from. Observation 3. Notice that the SS between is smaller than the SS within. So looking back at the ANOVA table, we have the SS between is 117.1, and the SS within is 492.8. The quote-unquote problem here is that SS within has more numbers to square and sum, so of course it's larger. Had I convinced more elves to appreciate the importance of this research, SS within could have been even larger, without the SS between changing at all. This highlights why these sum of squared terms need to be scaled by their corresponding degrees of freedom. The effect size, measured as omega squared, was 0.146, indicating that around 14% of the variability of spells cast was attributable to creature type. My interpretation of this effect size is that although the data do show that trolls cast the fewest spells, there is a lot of individual variability that is attributable to other factors. Clearly, further research is necessary to elucidate the reasons why some magical creatures cast spells faster than others. Raw data for this study are presented in Exercise 1. There, you will compute the ANOVA by implementing the formulas in Figure 14.5, and you will also perform post-hoc tests to compare these three groups. Section 14.7.1 ANOVA in Python. As with many other manual Python implementations of statistical procedures in this book, coding an ANOVA on your own is an amazing feat that you do once for the educational experience and to tell your grandmother about it so she can be proud of you and bake you cupcakes. After that, you used established libraries in Python or R or any other statistics program. There are two Python libraries that are commonly used to implement ANOVAs. Other libraries are either limited in scope or less often used. These libraries are Penguin and Stats Models. In this section, I will introduce you to using the Penguin library. Stats Models is used for more complicated ANOVA models and regression models, and I'll introduce it later in this chapter and in the next chapter. The Penguin library works only with pandas data frames. A one-way ANOVA requires a data frame with at least two columns, one column for the DV and one column for the IV. The data format is illustrated in Figure 14.10. Figure 14.10 shows an illustration of a data frame format for use with Penguin. Each observation is a row and contains the values for the DV and the IV. So the first column is the row index that we see that's typical for Python data frames. And then we have a column for spells and a column for creature. In other words, each individual observation has one row in this data frame. Back to the text. Thereafter, you call the ANOVA function, entering the name of the data frame variable and the names of the columns of the DV and between subjects factor. Figure 14.11 shows the code and output format. The optional input detailed equals true will return the within row. Note that Penguin does not print out the total row. This paragraph refers to Figure 14.11, which shows a screenshot of Google Colab showing code and the ANOVA table in our experiment. The code shows the variable result equals PG, this is typical abbreviation for the Penguin library, pg.ANOVA, the inputs data equals df, detailed equals true, dv equals spells in single quotes, and between equals creature in single quotes. And the result, the output of pg.ANOVA, is the ANOVA table, and we see a row for creature and a row for within. And we get an F value of 4.51 and a P value of 0.017411. Back to the text. I hope the labels in the columns in the output of pg.ANOVA are self-explanatory. The generic term between that I used earlier in this chapter is replaced with the specific factor name, in this case creature. P-unc stands for uncorrected p-value, and NP2 is eta squared partial, although for one-way ANOVA, this column reports the eta squared. It's interesting to compare eta squared equals 19% versus omega squared equals 14%. You will compute omega squared as part of exercise 1. We can attribute that difference to an inflation of estimated effect size in eta squared. That seems like a big difference, but with larger sample sizes, these two quantities converge. Section 14.7.2, ANOVA in R. Before proceeding to tell you how to implement a one-way ANOVA in R, I'd like to make a general remark about ANOVAs in R. R lacks a single, all-encompassing function that handles all variations of ANOVAs with different specifications and complexities. Instead, the choice of function or package in R for ANOVA depends on the specific type of the ANOVA, the design of your experiment, and the nature of your data. This means that in practice, you need to carefully consider your experiment design and hypotheses before deciding which function is most useful for each application. Below is a brief summary of ANOVA functions you are likely to encounter. I will introduce the functionality of several of these methods throughout the chapter. AOV. This is in base R. This is useful for one-way and two-way ANOVAs, both between subjects and within subjects. It has limited capabilities for complex designs, such as mixed effects models or when sphericity is violated. The function AOV is frequently used, and in the interest of consistency, I will use this function when possible throughout this chapter. Easy ANOVA in the Easy package. This is a more user-friendly routine for repeated measures ANOVA. It automatically checks for sphericity and applies corrections when appropriate. AOV_easy and mixed. These are both in the AFEX package. These functions are useful for various ANOVA types, including mixed designs. They test for sphericity violations and provide various corrections. They also provide detailed output and integrate with the EM_means function for post-hoc analyses. LME and LMER, both contained in the LME4 package. These functions can be used for simple ANOVA models, but are best suited for advanced designs, including hierarchical and mixed effects linear models. There are entire books dedicated to such advanced models, and I don't cover them here, although I will introduce you to the LME function for assessing pairwise comparisons in a repeated measures ANOVA. ANOVA in the CAR package. This function is used to implement type 2 and type 3 sum of squares, which makes this function useful for unbalanced designs in multi-way ANOVAs. The ANOVA function is also used to compare multiple nested models. LM and GLM in base R. These functions provide flexibility for specifying general linear models, which makes them useful for custom designs. Now I will show you how to implement a one-way ANOVA using the AOV function. The basic usage of AOV involves specifying a formula that characterizes the model using column labels of a data frame and the data frame that contains the data. For example, figure 14.12 shows code that performs a one-way ANOVA using a data frame labeled DF that contains columns with labels spells, the DV, and creature, the IV. You can see that the results are the same as those computed by Python in figure 14.11. There are small differences that are due to rounding errors, and they can be ignored. This paragraph refers to figure 14.12, which shows a screenshot of RStudio showing code and an ANOVA table. Here we see, in the screenshot, we see the R code with variable named ANOVA result equals AOV, and then the inputs are, first input is spells tilde creature, second input is data equals df. And then the next line of code is summary, the function summary with input ANOVA results. And then we see an ANOVA table with numbers that match the numbers that I showed earlier, both in the text and from the Python code. Back to the text. I believe that the columns of the ANOVA table returned by the summary function are self-explanatory. This summary does not include measures of effect size, but you can compute these by calling an additional function called eta squared, which is in the LSR library. Section 14.8, One-Way Repeated Measures ANOVA. I'm now going to pivot to other ANOVA flavors. Fortunately, the math underlying all ANOVAs is similar to what you learned above, just slightly more complicated because of the additional factors. Repeated measures ANOVA, often abbreviated RM-ANOVA, is used when the same individuals are measured at all levels of a factor. That is not the case in the magical beasts example because an elf cannot also be a troll, at least as far as I know. Here are a few examples of experiments in which a repeated measures ANOVA is an appropriate analysis. Example 1, cognitive therapy. A team of psychologists is testing the effectiveness of a new cognitive therapy technique to reduce symptoms of depression. They recruit 100 people diagnosed with depression and administer a standard depression inventory at the start of the study, that would be time 1, after 4 weeks of therapy, time 2, and after 8 weeks of therapy, time 3. The DV is depression score and the IV is time. Example 2, exercise warm-up. A group of exercise scientists is studying the effects of 3 different types of warm-up exercises on running performance. 50 runners complete a time trial after each type of warm-up on 3 separate days. The DV is running time, and the IV is the type of warm-up. Example 3, visual perception. A team of psychologists is studying the effect of colors on perceived attractiveness. They show participants images of the same object in red, blue, and green and ask them to rate the attractiveness of each object. The DV is attractiveness rating and the IV is the color of the object. Example 4, music preference. A group of researchers is interested in people's reactions to different genres of music. They play a clip of a song from the rock, classical, and pop genres and ask participants to rate how much they enjoy each song. The DV is the enjoyment rating and the IV is the genre of music. In the first 2 examples, the repeated measure was related to time, whereas in the last 2 examples, the repeated measure was sensory characteristics. An ANOVA in which each level has a different group of subjects, that is the opposite of an RM-ANOVA, is called an independent measures ANOVA or a between subjects ANOVA. If the ANOVA is not explicitly stated to be repeated measures, then you can assume it is a between subjects design. The null and alternative hypotheses of the repeated measures ANOVA are identical to those of the one-way ANOVA. The null hypothesis is that the means of all cells are equal, while the alternative hypothesis is that the mean of at least one cell is different from the mean of at least one other cell. Section 14.8.1, Advantages of RM-ANOVA. Repeated measures ANOVAs bring several statistical and experimental advantages, all of which stem from testing the same individuals repeatedly. Because each subject provides data for all levels, variability is reduced, thus increasing statistical power. This is similar to the reduction of variability in a paired samples t-test, and something you will empirically confirm in exercises 7 and 8. The upshot is that an RM-ANOVA is more sensitive to subtle effects. Relatedly, uncontrolled variables have a smaller impact because each participant serves as their own control. This allows for reduced sample sizes. Consider the exercise warm-up example above. Conducting this study as a between subjects ANOVA would require 150 runners, whereas the repeated measures ANOVA requires only 50 runners. This advantage of repeated measures ANOVA is particularly relevant for studies that are expensive or time-consuming to conduct. In short, repeated measures ANOVAs are preferred over between subjects ANOVAs and should be used when the research topic allows it. Section 14.8.2, the math of a repeated measures ANOVA. The concept of the RM-ANOVA, and in particular the calculation of the F-statistic, is the same as with the independent samples ANOVA. It's the ratio of explained to unexplained variability. However, the variability attributable to subject, that is, the individuals from whom we take the repeated measurements, can be sliced out of the SS within term, which means that more variability can be explained, and by the same token, less variability is left unexplained. This paragraph refers to figure 14.13, which illustrates the conceptual idea of partitioning variability in the repeated measures ANOVA. The total variability is separated into what can be explained and what cannot be explained, and the F-statistic is the ratio of those. Now, we have two pie charts here, on the left and on the right. The pie chart on the left indicates the independent samples ANOVA, which I already explained. In this case, the data variability is either between conditions or within condition. However, in a repeated measures ANOVA, this is the pie chart on the right, variability attributable to subject can be carved out of SS within. And in this diagram, this set of pie charts, what I've illustrated is that the SS between is the same size in both pies, while the SS within actually shrinks for the repeated measures ANOVA because part of that variability can be accounted for with SS subjects, or the variability attributable to subjects. And this means that the F ratio will actually be larger in the repeated measures ANOVA compared to the independent samples ANOVA. Back to the text. The formula for SS subjects looks really similar to the formula for SS between. Here's both of them. Here we have two equations. Equation 14.18 states SS between equals n times the sum from j equals 1 to k of the quantity x sub j bar minus x bar, and that quantity squared, with degrees of freedom corresponding to k minus 1. Then we have the next equation, equation 14.19, that states SS subjects equals the sum from I equals 1 to n, capital N over all of the subjects in the experiment, of the quantity x sub I bar minus x bar, and that quantity squared, with n minus 1 degrees of freedom. Back to the text. At first glance, the two equations look nearly identical. They are both sums of squares, and the variability in both cases reflects a spread around the grand mean, or x bar. But there is an important distinction. SS between measures the dispersion of level averages while ignoring variability across subjects, whereas SS subjects measures the dispersion of subject averages while ignoring levels. This difference is also reflected in their degrees of freedom. SS between has k minus 1 degrees of freedom from k levels, whereas SS subjects has n minus 1 degrees of freedom from n subjects. SS between is slightly different here compared to the independent samples ANOVA. That's exactly what I discussed earlier in the chapter. The independent samples sum of squares scales by n sub j, whereas the repeated measures sum of squares scales by capital N. The repeated measures ANOVA does not have an n sub j term because each subject provides data for each level. With this newest member of the SS team, we can redefine the total variability in the dataset. Here we have equation 14.20, which reads SS total equals SS between plus SS subjects plus SS within. This is a simple formula, and we can define any one variable as a function of the others. For example, we can compute SS within according to equation 14.21, which reads SS within equals SS total minus SS between minus SS subjects. I like this formulation because it clarifies the idea of SS within. Take the entirety of the data variability, remove the variability that is attributable to the experiment and to individual differences, and whatever's left is the unexplained variability. Now, with all that in mind, you're now ready to see the ANOVA table. Notice that this table has 4 rows compared to 3 rows for the independent samples one-way ANOVA. This paragraph refers to figure 14.14, which shows a one-way repeated measures ANOVA table. This basically just summarizes all of the SS and MS formulas with their degrees of freedom that I have already described. There are 4 rows in this table, corresponding to between sum of squares, subjects sum of squares, within sum of squares, and the total sum of squares. What is noteworthy here is that we have 2 values for F scores. So there are 2 rows that have an F score. We have F for between and F for subjects. Back to the text. The DF total, so degrees of freedom for the total sum of squares, is n times k minus 1 instead of n minus 1. That's because the total number of data points is not the total number of subjects, but the total number of subjects times the number of measurements per subject. There are 2 F statistics, one for the main effect of the experimental factor and one for subjects. That latter F statistic is usually not reported or interpreted. A statistically significant F score for subjects indicates that the differences across subjects are larger than the unexplainable variability. In most cases, the subjects factor is included in the ANOVA only to slice variability away from the within piece of the pie. Section 14.8.3, Example One-Way Repeated Measures ANOVA. Everyone likes to snack, and everyone likes to be in a good mood. Of course, you don't eat snack food all the time, and you're not in a good mood all the time. Is there a relationship between snack food type and mood? Let's do a fake research study to find out, and also to learn about one-way repeated measures ANOVA. In our fake study, we asked 8 participants to spend 2 days eating each of 3 snack foods: chocolate, potato chips, or crisps, as the Brits would say, and ice cream. At the end of each 2-day session, they reported their mood. They also reported their mood before any of the sessions began. Now, in a real study, you would want to control for the ordering of snacks and so on, but we don't need to worry about sequence effects in this fake study. Data organization. ANOVA data can be organized into quote-unquote wide format or quote-unquote long format. In wide format, each variable or condition is given its own column, and each row corresponds to a unique subject or participant. The data table contains n rows. By contrast, in long format, each participant's data spans k rows corresponding to k measurements. A long format data table contains n times k rows and 3 columns, with columns corresponding to the subject ID, the level, and the dependent variable. A long format data table for a two-way repeated measures ANOVA would have 4 columns, one for each factor. This paragraph references two figures. Figure 14.15 shows data in wide format. Here we see a screenshot of a data table from Python. It is a table with 8 rows, 1 row per participant, and 5 columns. There's 1 column for the participant identifier. This is labeled as P1, P2, P3, and so on up to P8 for 8 participants. And then we have 4 columns corresponding to the 4 variables, the 4 conditions. That's baseline, chips, chocolate, and ice cream. So that's data in wide format. Then we have figure 14.16, which illustrates data in long format. Here we have many rows. I'm only showing a selection of rows. And then there are 4 columns. The first column is just the row index. It's 0, 4, 8, 12, and so on. The second column is the participant label, so P1, P5, P1, and so on. And then the third column indicates the level of the factor, so that's baseline, baseline, chocolate, chocolate chips, and so on. And then the final column is for the mood, which is a number, and here it's 5, 6, 8, and so on. So the idea of data in long format is that each participant actually spans multiple rows. So in this image, we see that participant P1 spans at least 4 rows that are shown in this figure, corresponding to our 1 row per level of the factor. Back to the text. The process of converting from wide format to long format is called melting or stacking, while the process of converting from long format to wide format is called pivoting or casting. The appropriate format often depends on the analysis to be performed and the specific tools being used, as some functions prefer one format over the other. For example, many functions in Pandas and Seaborn assume long format, while some traditional statistical software packages like SPSS use wide format. Repeated measures ANOVA in Python. RM-ANOVAs are easy to implement in the Penguin library. In the code shown in figure 14.17, the data are stored in a pandas data frame, that's variable df, and the other inputs correspond to the names of the columns. This paragraph references figure 14.17, which shows an example of Python code and output to implement a one-way repeated measures ANOVA. The code is variable RM-ANOVA equals PG for penguin, pg.rm_ANOVA with inputs data equals df, dv equals mood, within equals snack, subject equals participant, and detailed equals true. The output variable shows a table of the ANOVA table with an F value of around 24 and a P value that is less than 0.05. Back to the text. In the RM-ANOVA function, you specify the repeated factor, in this case that's within, and the subject's factor. Notice that even though I selected detailed equals true, the ANOVA table does not show the F statistic for the subject's factor or a row for the total SS. In this data set, we have F of 3 and 21 equals 24, P less than 0.001. This demonstrates that snack food type affects mood. But which snack foods affect mood in which ways? The F statistic does not provide this information. Therefore, we need to visualize these data. The box plots in figure 14.18 show that chocolate and ice cream increase mood, whereas chips decrease mood relative to baseline. This paragraph references figure 14.18, which shows data from the snack mood study. Of course, these are all fake data. I just made up all the numbers. Okay, so we have a series of box plots where there are 4 box plots corresponding to, on the x-axis, ticks, baseline, chocolate, chips, and ice cream. The y-axis shows mood, and what we see is that baseline has an average of somewhere around 6.5. Chocolate is higher at around 7.5. Chips is below baseline at around 5.5. And ice cream is all the way up there at an average mood of somewhere around 8. LOL. Or is that pronounced lol? Anyway, back to the text. Visualizing the data helps us interpret the direction of the effect, but doesn't tell us which conditions are statistically significantly different from which others. For that, we need to perform a post-hoc test. I implemented a post-hoc comparison using the pairwise tests function in the Penguin library. The code is below. Function is pg.pairwise-tests. Inputs are data equals df, dv equals mood, within equals snack, subject equals participant, and p-adjust equals Bonferroni. The input, p-adjust, allows you to specify the method for multiple comparisons correction. Here I used Bonferroni correction. You can specify FDR_BH for FDR correction, or one of several other correction methods, and you can check out the documentation of this function. The table below shows the results. Here we have a table that contains 6 rows, 1 row for each possible comparison. For example, the first row is baseline versus chips, the second row corresponds to baseline versus chocolate, and so on. Then we see in columns are the t-value, the degrees of freedom, the uncorrected p-values, the corrected p-values, a Bayes factor column labeled BF10, and something called hedges, which I will mention in a moment. Back to the text. I've modified the table slightly to remove some columns and truncate numbers so that it fits in the book page. Each row shows a comparison between 2 levels. P-core is the statistical significance to pay attention to. If this is less than 0.05, you can interpret the result, and the sign of the t-value indicates the direction of the effect, with the numerator of the test being A minus B, where A and B correspond to the first 2 columns of this table. BF10 is a Bayes factor that's not discussed here, and hedges is a measure of effect size comparable to Cohen's d. These findings reveal that chocolate and ice cream improved mood, whereas snacking on chips decreased mood relative to chocolate and ice cream, but not relative to baseline. This latter finding is curious. Post-chip mood numerically decreases relative to baseline, but the effect is not statistically significant. On the other hand, chip-induced mood is statistically significantly lower than chocolate or ice cream-induced mood. This kind of pattern can be difficult to interpret, but it happens in real data. Anyway, the point is to continue eating chocolate and or ice cream, but hold off on the chips. Footnote. Yeah, these are all fake data, so these conclusions are fake news. Nota bene, I received no funding from the chocolate or ice cream industries, not even free samples. Insert sad emoji. Back to the text. RM-ANOVA in R. You can run a repeated measures ANOVA using the AOV function by specifying the error term in the model specification, which you can see in figure 14.19. This paragraph references figure 14.19, which shows a screenshot of calling and viewing the results of a repeated measures ANOVA in R. The function is AOV, and the inputs are mood tilde snack plus error, and then in parentheses participant divided by snack, end parentheses, comma, df. The summary of this variable RM-ANOVA, that is the output of the AOV function, shows a table of the ANOVA results, including an F value of 24 with a p-value that is much less than 0.01. Back to the text. The additional term compared to the one-way ANOVA code is error parenthesis participant divided by snack. In this data frame, snack is the column label of the IV, and participant is the label of the column that indicates which row of the data comes from which participant. In this example, each participant was measured 4 times, and the column participant indicates which rows are associated with which subjects. The error term contains 2 column labels, and the slash notation indicates that one is nested inside the other. Thus, each unique value of participant has multiple measurements for the factor snack. That is, each subject received all snacks. The code and output below shows the table of pairwise comparisons using Bonferroni correction. This matches the output of the Python approach. Here we have output variable pairwise tests equals data of pairwise t-test, and then inputs mood tilde snack paired equals true, and p.adjust.method equals Bonferroni. This gives us the same table that I described for the output from the Python function. Briefly, we have a table with 6 rows, where each row corresponds to a comparison between each of the groups, so baseline versus chips, baseline versus chocolate, and so on. And we see the statistical value, which is in this case the t-value, degrees of freedom, corrected and uncorrected p-value, and significance. Section 14.9, ANOVA residuals. Now you've inspected and interpreted the ANOVA table. Aside from the F and P values, how can you evaluate whether the model is a good fit to the data? The answer, as you might have guessed from the title of this section, is to inspect the residuals of the model. The main take-home message of this section is that the residuals should look like a random blob that lacks any visual or statistical evidence of structure other than normality. This should be the case if your data meet the ANOVA assumptions and if the model is sensible given the data. That is, you have good hypotheses and properly translated those hypotheses into a mathematical model. Inspecting the residuals is a good way to evaluate how the model relates to the data. Section 14.9.1, Calculate the residuals. I introduced the idea of residuals in section 14.3.1. Here's a reminder and a new equation. Here we have 2 equations. The first is a repeat of equation 14.1, which reads x sub ij equals x bar sub j plus epsilon sub ij. Now we have a new equation, 14.22, which is epsilon sub ij equals x bar sub j minus x sub ij. It's actually just rewriting the previous equation. Back to the text. In other words, the residual for each data point is the predicted value minus the observed value. The function pg.RM-ANOVA doesn't return the residuals or the predicted values, so we compute them manually. This simply involves subtracting the observed data values from their respective cell means. The code below illustrates the procedure for our snacks study. So we have the variable group means equals df, that's from variable data frame, df.group by, and then in parentheses snack, and then we have mood selecting for mood dot mean. Then we add a column of predicted data, so that's df, and then a new column predicted, equals df snack dot map group means. And then we create a column of the residuals, that's df, a new column for residual, equals df column for mood minus df column for predicted. You can see a few rows of the updated dataset in Figure 14.20. Figure 14.20 shows a screenshot of a data frame in Python, but in R it looks basically the same, and that is the dataset with predicted values and residuals. These data show long format, so we have columns corresponding to participant, snack, mood. That was what I already described in a previous figure. And now we have two new columns for predicted and residual. Section 14.9.2, Inspect the residuals. Now you have the residuals, what do you do with them? Here are some suggestions. Suggestion 1, inspect the distribution for Gaussianity. The residuals should be roughly Gaussian distributed. You can inspect them using a histogram. Suggestion 2, plot the residuals versus the predicted values. In this plot, the residuals should be randomly distributed around the y=0 line, and the variability should be the same for the entire range of predicted values. This would indicate homoscedasticity, which means that the residuals have constant variance across different levels of the predicted values. A clear pattern in the residuals, like a funnel shape, where the dispersion of the residuals changes with the predicted values, indicates heteroscedasticity and is a violation of one of the assumptions of ANOVA. Suggestion 3, QQ plot. If the residuals are normally distributed, they should roughly follow the diagonal line. These three metrics are shown in Figure 14.21 for the snack study data. Now, the histogram may not look convincingly Gaussian, but this is a small dataset comprising fake data. Anyway, the residuals and QQ plots look good. This paragraph references Figure 14.21, which illustrates a visual inspection of the model residuals. The figure contains 3 panels. The first panel on the left shows a residuals histogram, and there's only 5 bins, but it looks sort of Gaussian-ish, although the leftmost bin is a bit higher than what you'd expect for Gaussian. Panel B in the middle shows the residuals versus y-hat. So we have the predicted values on the x-axis and the residuals on the y-axis. And what we see is kind of like a cloud. In this particular case, there are only 4 possible values of the predicted data, but that's more a reflection of the small sample size and not so much a reflection of something wrong with the data. And then in panel C on the right, we have a QQ plot, and here we see that the residuals fall nicely on the diagonal line as would be expected for a normal distribution. Back to the text. Residuals plots provide qualitative information about the validity of the assumptions. Violations of the independence assumption can be hard to detect visually, and statistical tests of normality can facilitate a more rigorous examination. On the other hand, tests of normality can be significant, indicating lack of normality, for very large samples, as I discussed in section 11.1.9. Sometimes statistics is more of an art than a science. Section 14.9.3, what to do when the residuals are non-Gaussian. Patterns in the residuals, such as a non-Gaussian distribution or heteroscedasticity, indicate violations of ANOVA assumptions. These violations can potentially bias your results, so they should be addressed. Here are some approaches you can consider. Approach 1. Apply data transformations. Depending on the specific pattern of residuals, nonlinear data transformations may help. For example, if the residuals show a pattern of increasing variance with the value of the dv, a log or square root transformation might be justified. Approach 2. Remove outliers. Check or recheck the data for outliers and test whether removing outliers improves the fit of the model. This must be done carefully because selecting data after having seen the results risks introducing systematic biases. Approach 3. Use non-parametric methods. If the data do not meet the assumption of normality, non-parametric methods may be a good alternative. I will introduce non-parametric ANOVA alternatives towards the end of this chapter. Approach 4. Use more sophisticated models. More sophisticated statistical models, such as linear mixed effects models, can handle more complex error structures and may be a good alternative if the residuals from an ANOVA show clear patterns. I do not discuss these models in this book, although learning about ANOVA and regression will help you understand linear mixed effects models. Finally, it is worth mentioning that the importance of these assumptions can depend on the size of your dataset. With large datasets, minor violations of assumptions may have an inconsequential impact on the results. However, with smaller datasets, such violations can be more problematic. Section 14.10, the two-way ANOVA. A two-way ANOVA is more than twice as complicated as a one-way ANOVA. The reason is that the factors can interact with each other. In this section, I will introduce the interpretations of two-way ANOVAs and show how the math of the one-way ANOVA is extended into the two-way case. The concepts and interpretations are more important here because the exact formulas will change depending on whether the design is balanced and whether there is a repeated measures factor. Section 14.10.1, Interpreting Main Effects and Interactions. You already know about the main effects. That's the factor in the ANOVA that you experimentally manipulated or observed. An interaction is when two or more factors affect each other. For example, imagine a medical study that tests whether a new medication improves cardiovascular health. The research involves giving the medication or a placebo to young and old people. The factors are medication, real versus placebo, and age, young versus old. Thus, a 2x2 ANOVA. What if the medication works differently in younger versus older people? This would be an interaction between the two factors. I will explain the math of the interaction term in a few pages, but it's computed by summing up all of the variability inside one cell, for example, young people taking placebo, and then removing any variability that can be attributed only to the medication and only to the age group. The interaction term has its own SS and MS values and therefore produces its own F statistic. Interaction terms can be tricky. Indeed, if the interaction term is statistically significant, you cannot interpret the main effects without visualizing the data. Interactions are indicated using a multiplication sign. This is not the same as the letter X, but it's fine to use the letter X if you don't have ready access to a multiplication sign. The reason for indicating interactions using a multiplication sign is that multiplication is literally how you create an interaction term in general linear models like regression, which you'll learn about in the next chapter. The following list refers to figure 14.22. These are all fake data that illustrate possible patterns in a two-way ANOVA using the example study I mentioned above. I will describe each of these panels after first reading the relevant text. First, we have main effects without an interaction. This is shown in panel A of figure 14.22. This is the easiest pattern of results to interpret. Cardiovascular health is better in young compared to old people, but medication has no impact in either group. You could imagine another scenario of a main effect of medication in which both gray bars were higher than the black bars. That is not actually shown here. So this paragraph refers to panel A of figure 14.22. Here we see 4 bars in 2 groups. We have a group for young people and a group for old people. And then within each of those age groups, we have a black bar corresponding to placebo and a gray bar corresponding to medication. The y-axis is CV health for cardiovascular health. And in this panel, we have the 2 bars being equally high for young people and equally lower for old people. Thus, there is a main effect of age group, but no effect of medication and no interaction. Back to the text. 2 main effects with an interaction in panel B. You need to be careful when interpreting main effects in the presence of a significant interaction term. In this example, the F statistic for the main effect of medication is statistically significant, which would make you think that medication improved CV health for everyone. But the bar plots show a different story. Medication only improved health for older people. Thus, the main effect of medication cannot be interpreted on its own because of the interaction. Based on the bar graph, you might be surprised that the main effect is significant, but remember that a main effect of one factor ignores the other factor. Here, the average of the gray bars is significantly higher than the average of the black bars. On the other hand, the main effect of age is interpretable on its own. CV health is better in young compared to older people, averaging over the effect of the medication. The conclusion from this example is that the main effects might be, or might not be, interpretable in the presence of an interaction term, and you won't know until you visualize the data. This paragraph references panel B of figure 14.22. The concept that is illustrated here is an interaction between the 2 factors, age and medication. The overall characteristics of the bar plot are the same as panel A, so 4 bars in 2 groups for young and old on the left and right side of the x-axis, and then we have black bars for placebo and gray bars for medication. What we see in this panel is that the young group has equally high bars for placebo and medication, so medication had no impact on CV health for young people, whereas for old people, we see that the gray bar is significantly higher than the black bar, indicating that the medication improves CV health in old people. And then we see the main effect of the age group is illustrated by both of the old bars being lower than both of the young bars. Back to the text. Interaction term without main effects. This is shown in panel C. Here again, you see that an interaction term cannot be interpreted without visualizing the data. There is no main effect of age, so old people have lower CV health numerically but not statistically, and no main effect of medication, but the interaction reveals that the medication does have an effect. It improves CV health for old people, but impairs CV health for young people. This pattern is called a crossover interaction, and such a pattern does have precedent. Many medications, including treatments for mental health conditions, affect children and adults differently. This paragraph refers to panel C of figure 14.22. Here we see that the black bar for young is higher compared to the gray bar for young, but when we look at the old group, we see that the black bar is lower than it is for the old people. In other words, there is a crossover interaction such that the medication either improved or impaired CV health depending on the age group. Section 14.10.2, the math of the two-way ANOVA. The equations below show the SS terms. I will provide written explanations of them over the next few pages, but I would like you to inspect the equations on your own first and see if you can make sense of them. Now, the exact equations for a two-way ANOVA depend on whether the groups are balanced, whether there are repeated measurements, and on the order in which the sum of squares for each factor are calculated. I will discuss some of these complexities later. For now, you should focus on the concepts and not on memorizing formulas. Here we have 5 equations. Now, these equations are relatively involved. I'm not going to read all of them. I recommend getting a copy of the book and inspecting these equations. It's equation 14.23 through 14.27. These are the equations for the sum of squared terms for a two-way ANOVA with an interaction. So we have sum of squared between for factor A, sum of squared between for factor B, sum of squares of the interaction term between A and B, and then sum of squares within and sum of squares total. Back to the text. There's a lot going on there. Let me make a few comments to help you read the equations, and then I'll write plain English sentences to help you interpret those equations. Comment 1. A is the number of levels in factor A, and B is the number of levels in factor B. Comment 2. N sub A dot is the total number of observations in the AF level of factor A, aggregating across levels of B. N sub dot B is the total number of observations in the Bth level of factor B, aggregating across levels of A. And N sub AB is the number of observations in the Ath level of factor A and the Bth level of factor B. Comment 3. X sub IAB is the data value from subject I in level A of factor A and level B of factor B. Comment 4. X bar is the grand mean of the entire data set, so all levels of all factors. Comment 5. You might think I made a typo in equation 14.25 with adding X bar. Understanding why the grand mean is added back will actually help you understand the interaction term. Consider that each cell in the factorial design table contains variability due to A, variability due to B, and variability to the interaction between A and B. In order to isolate the unique interaction-related variability in that cell, we compute the total variability and subtract off the variability due to the factors on their own. In particular, we can define SS A times B as the sum of the SS for this cell minus SS between A and minus SS between B. So each of these SS terms includes subtracting off X bar, and so the equation has one negative X bar and two positive X bars, giving us a total of one positive X bar. In other words, there is a double subtraction of the grand average. Comment 5. The df parameter of sum of squared within may look confusing. Recall the idea that df, degrees of freedom, is the number of data values minus the number of means. In this case, we have the degrees of freedom for the total number of observations, that's capital N minus 1, and subtract the df for the total number of cells for which we compute the average, so that's A times B minus 1. So the df is N minus 1 minus the quantity AB minus 1. And then there's some arithmetic cancellation to get A, N minus AB. This assumes a balanced design, that is, capital N equals A times B times lowercase n. The degrees of freedom parameter will be different if each cell has a different number of observations. Final comment. The degrees of freedom of the sum of squares total is the total number of observations. For an independent samples two-way ANOVA, each subject provides exactly one observation, corresponding to df equals n minus 1. If one of the factors is a repeated measure, and or if the design is unbalanced, then the df would be something more complicated along the lines of the sum of little n sub ab. The point is, well, honestly, the point is that the math underlying multifactorial ANOVAs gets complicated quickly. Okay, and now for the plain English explanations of each of those equations. SS between A. This equation calculates the between subject sum of squares for factor A. It quantifies the amount of variability in the data that can be explained by different levels of factor A. It does this by summing up the squared differences between each level's mean, ignoring factor B, and the overall grand mean, scaled up by the number of observations in each group. SS between B. Similar to SS between A, but for factor B. It measures how much of the total variability in the data is attributable to differences between the levels of factor B, ignoring factor A. Sum of squares A times B. This measures whether one factor modulates the impact of the other factor. It calculates how much of the variability in the data can be explained by the combined effect of factors A and B that cannot be explained by either factor alone. It does this by summing up the squared differences between the means of each cell, which is one pairing of levels A and B, and the grand mean, and then subtracting the variability attributable individually to factors A and B. If there is no interaction and all within cell variability is due to independent contributions from factors A and B, then SS A times B goes to 0. As with the other sum of squared terms, the interaction SS is scaled up by the sample size within each cell. SS within. This is the within group SS. As with the one-way ANOVA, it quantifies the amount of variability in the data that cannot be explained by factor A, factor B, or their interaction. Also, as with one-way ANOVA, it's sometimes called the error or the residual sum of squares. Equation 14.27 shows the calculation as summing the squared differences between each individual observation and the group mean for that observation's combination of A and B levels. However, it can also be calculated as the residual variability not accounted for by the design, which is the sum of squares total minus the two between and the interaction SS terms. SS total. Same as the SS total term from the one-way ANOVA, it represents the total variability in the data, ignoring all experiment factors and interactions. It is calculated by summing the squared differences between each individual observation and the grand mean. Note the absence of an little n scaling factor here and also for the sum of squared within. These terms are already trivially going to increase with sample size because of the summation over subjects. You can see that with the I subscript. Okay, in the interest of preserving your sanity and mine, I do not recommend computing a two-way ANOVA by hand. I also do not recommend writing Python code to implement the two-way ANOVA because the risk of a coding mistake is just too high. However, I do hope that you spend enough time thinking about the sum of squared equations and the rest of the ANOVA table to understand the concepts and mechanisms of the ANOVA and how the two-way ANOVA is an extension of the one-way ANOVA. This paragraph references figure 14.23, which shows a two-way ANOVA table. The table has 5 rows corresponding to the different sources of the sum of squares. So, sum of squares between A, between B, the interaction between A and B, within, and total. And then we have extra columns for the degrees of freedom, the mean square, and the F statistic ratios. This is actually just a summary of what you have already learned in this section. Back to the text. Section 14.10.3, how many ways? How many factors can you have in an ANOVA? The sky's the limit as long as you have a big enough sample size. But every factor you add makes the ANOVA exponentially more complicated to interpret. A three-way ANOVA has three main effects and four interaction terms. That is the interaction between A and B, between A and C, between B and C, and between A, B, and C. Unless you have a really specific hypothesis, interpreting all of those effects is challenging, though within the realm of human intellectual capabilities. I don't even want to think about a five-way ANOVA. That is truly the stuff of nightmares. Section 14.11, types of sums of squares. There are three ways of partitioning the sum of squares in a multifactorial ANOVA, that is a two-way or higher. Those quote-unquote types are relevant when there are interactions and or unbalanced designs. Why are there different types? Well, the reason is that if the factors are correlated, or if the data are correlated across factors even due to random sampling variability, then the SS terms can have redundant variability. In other words, if factors A and B have non-zero covariance, then SS between A and SS between B will have overlapping variability, which means that their F ratios will be partially redundant, which also means that the interaction term may be incorrectly specified. As an illustrative example, imagine we have a two-way ANOVA with factor A having two levels corresponding to age groups 30 to 50 and 50 to 80, and factor B having three levels corresponding to age groups 30 to 45, 45 to 65, and 65 to 80. Obviously, this is a terrible design because the two factors are highly correlated. Most of the variability in factor A is also present in factor B. It would be impossible to interpret the main effects separately, and the interaction term would be completely meaningless. Okay, that's an extreme example. Here's a better example. Let's imagine a study about the effects of aspirin and home location, so urban versus rural, on cardiovascular health. We randomly select elderly people matching for age, education, and wealth, and measure cardiovascular health before and after giving them a daily dose of aspirin or placebo for 2 weeks. On the one hand, the two factors, so home location and aspirin versus placebo, should be independent because we randomly assign people to be in the aspirin or placebo group. But it is possible that the two factors share some variance. For example, if there is something about living in an urban area or people who choose to live in an urban area that affects how the body metabolizes aspirin, this creates shared variability between factors. How to deal with this shared variability? Well, the best approach is to avoid it in the first place by setting up the experiment such that the factors truly are independent. But that is not always feasible. The second best way to deal with shared variability is by statistically removing it. This means to compute the SS for one factor after controlling for or accounting for the other factor. That's done by calculating the SS not on the raw data, but on the residuals from the other factor. For example, we can compute SS medication using the residuals from the factor location. If medication and location were truly independent of each other, then SS medication would be the same, regardless of whether it is computed on the raw data or on the residuals of SS location. On the other hand, if the two factors shared some variability, then the SS computed from the residuals would be smaller than the SS computed from the raw data. But This means that the order in which we compute the SS terms can change the results. That is, the SS of SS medication could depend on whether we compute SS medication first using the raw data, or whether we compute SS medication on the residuals of SS location. If the factors are truly independent and balanced, then the order doesn't matter. Going back to the terrible design with the two factors using differently sliced age groups, SS for factor B will be close to 0 when computed on the residuals of SS for factor A, but will be much larger when computed on the raw data. And this leads us to the three types of ANOVA sum of squares calculations. Below are overviews and descriptions of the three types. There is no clear correct or incorrect method, although type 3 is commonly used in designs with an interaction term. The Penguin library in Python implements type 2 by default. This can be specified with an optional ss_type argument, while the AOV function in R implements type 1 by default, and types 2 and 3 can be specified using the ANOVA function. You'll explore the implementation and impact of these types in exercise 9. Type 1, which is also called sequential. This approach calculates the sum of squares sequentially. It begins by considering the effect of one factor, then the effect of the next factor after accounting for the previous factor, and so on. For balanced designs, so that is, each group has the same number of observations, type 1 and type 3 sum of squares typically yield the same results. However, for unbalanced designs, the order in which factors are entered can have a bigger impact because of how the means are calculated within versus across levels. Now, this can lead to potential issues as the sum of squared attributed to a factor, and therefore potentially the statistical significance of the effect, can be different depending on the order in which it is considered. Next, we have type 2. This approach calculates the sum of squares for each factor after accounting for all other main effects, but not their interactions. It can have higher sensitivity to detecting main effects when the interactions are not included in the model or are expected to be non-significant, but it can lead to misspecifications of the interaction terms. And then we have type 3, which is also called partial. Type 3 sum of squares calculates the unique contribution of each factor after accounting for all other factors and interactions in the model. This method is generally recommended when you are interested in maximizing sensitivity to detecting interactions. In many cases, especially if the design is perfectly or nearly balanced and the factors are unrelated to each other, the results from the ANOVA will be qualitatively the same regardless of which type you use. That is, the exact numerical results may differ, but you would come to the same statistical conclusion. If you're unsure which type to use, especially if you have a multifactorial ANOVA and are interested in the interaction terms, then you should use type 3. I am not going to write out all the various formulas because there are many and they get complicated to look at. But the equations are essentially the same as what I showed previously, except that residuals are used instead of raw data values, and adjustments are made for subtracting cell and grand means. Section 4.12, Sphericity and its corrections. Margin note. Sphericity is only relevant for repeated measures factors. Sphericity is an assumption in repeated measures ANOVA that concerns the variances of the differences between conditions. Specifically, it assumes that the variances of the pairwise differences amongst levels of a repeated measure are equal. Consider an ANOVA testing the effect of background music on reading comprehension. Participants read text while one of 3 different genres of music play in the background. That's the independent variable. And then the participants take a comprehension test. That's the dependent variable. In this repeated measures design, every participant listens to all music genres in different sessions, leading to correlated measures. Now, sphericity is about the variances of the differences between those conditions. That is, the variance of the difference in comprehension scores between genres 1 and 2 should be roughly equal to the variance of the difference between genres 1 and 3, which should be roughly equal to the variance of the difference between genres 3 and 4. Violating the assumption of sphericity can lead to biases in the f-tests. Specifically, the ANOVA might show significance when there isn't any, increasing the type 1 error rate. To assess sphericity in your data, you can use Mauchly's test. I described this below. If your data violate the sphericity assumption, you can adjust the degrees of freedom of your f-test using a correction, such as the Greenhouse-Geyser correction or Hunfeld correction. Both of these corrections make the f-tests more robust to the violation of sphericity assumption. The sphericity assumption does not apply to a between subjects design. Instead, the corresponding assumption is homogeneity of variances across the groups. That is, that each group has the same variance. And this can be tested with Levine's test or Bartlett's test. Section 14.12.1, Mauchly's test. Mauchly's test is used to evaluate the null hypothesis that the variances of the differences between all possible pairs of within subjects conditions are equal. That's a mouthful, but it's the same thing as saying that the assumption of sphericity holds. If Mauchly's test is statistically significant, we reject the null hypothesis and conclude that the sphericity assumption has been violated. The mechanics of Mauchly's test involve concepts in linear algebra. I will describe the procedure below, but if you're not familiar with linear algebra, then don't stress about the details. A geometric interpretation of a covariance matrix is that the matrix describes a hyperellipsoid with the directions of orthogonal maximal covariance indicated by the eigenvectors of the matrix, and the extent of those directions indicated by the eigenvalues of the matrix. If all eigenvalues of the covariance matrix are roughly equal, then the hyperellipsoid is a sphere or hypersphere. The test statistic of Mauchly's test, termed W, is the ratio of the observed determinant to the determinant that would be expected under perfect sphericity, and this would give the maximal possible determinant. That ratio ranges from 0 to 1, and the closer it is to 1, the more evidence there is for sphericity. The null hypothesis of Mauchly's test is that the data conform to sphericity, and so a p-value less than 0.05 indicates that the assumption of sphericity has been violated. It's another one of those situations where you hope that the test statistic is non-significant. A significant violation of sphericity does not invalidate the ANOVA results. Instead, you just have to adjust the degrees of freedom to control for inflated type 1 error rates. The RM-ANOVA function in the Penguin library includes an option to perform the Mauchly's test and use the Greenhouse-Geyser corrected p-value. There are also tests included in the R-AOV function. Section 14.13, Simulating Data for ANOVAs. You are well aware by this point in the book that I believe that simulating data is a great way to gain intuition about statistical analyses. The purpose of this section is to show you how to simulate data for various ANOVA situations. Developing the skill to simulate data for ANOVAs will help you understand the relationship between population means, sampling variability, main effects and interactions, and the elements in the ANOVA table. Having code and knowledge to simulate ANOVA data will also allow you to understand the impact of violating assumptions of ANOVA by being able to selectively and precisely manipulate data characteristics such as distribution shape, standard deviation, and the presence of outliers. For all the data, data within certain factors or data within certain levels of one factor. Section 14.13.1, Simulation 1, One-Way ANOVA. There are several ways to create a dataset for a one-way ANOVA. Here I will illustrate one method, and I'll use a simpler approach in some of the exercises just to add some variety and give you options. Figure 14.24a shows an example dataset. Each row contains the group assignment and the data value from one individual. Because each subject is measured only once, we do not need a subject identifier. That is, the fourth row contains data from subject number 4. This paragraph references figure 14.24, which shows simulated data for a one-way ANOVA. There are two panels. Panel A on the left shows a 2-column table where the left column is labeled group and the rows are 0, 1, 2, 0, 1, 2, 0, 1, 2, so 3 groups. And the right column is labeled value and has numbers like 1.44, 1.06, and so on. And then panel B to the right shows box plots of the 3 different groups. The values range from around -2 to +2, and well, there's nothing super interesting in this plot. These are just simulated data. Back to the text. Here's the code to set up the data creation. We have 4 lines of Python code where we indicate the level means. This is a 3-element list. The number of levels, that's just the length of level means. The sample size, which is the number of samples per level, and here I set this to 34. And then I have the number of data rows, which is the sample size times the number of levels. And then basically those same 4 lines of code are repeated in our syntax. This code initializes 3 levels with 34 subjects per level, which means the data set will have 34 times 3 equals 102 rows. This is a balanced ANOVA. The variable level means specifies the theoretical population means of each level. Of course, the sample means won't match those values exactly due to sampling variability and noise. Next, we create a vector of condition labels. So here we have 2 lines of code, 1 line for Python using the tile function and 1 line for R, that is using the rep function. This code creates the vector 0, 1, 2, and then repeats that vector 34 times. The result is the vector 0, 1, 2, 0, 1, 2, and so on. And you can see that in the first column of figure 14.24a. Now we are ready to create the data. The data are generated as normally distributed random numbers, with each level having its own mean. One way to accomplish this is to generate 102 normally distributed numbers and then multiply that by that vector by a Boolean mask for the group assignment. Here's the Python code implementation. I have initialize a variable call data for column data corresponding to the number of rows in the data set. And then we have a for loop over the number of levels. Inside that for loop, I first create a Boolean mask, which I call the variable which rows, and that is where group column equals I, and I is the looping index over the number of levels, so 0, 1, or 2. Then I extract the population cell mean, that is the indexed value from the variable list level means, and then I generate random data for those rows using the numpy.random.normal function, multiplied by the mask that I created 2 lines above. And then I have some R code which implements the same concept. Back to the text. In this loop over the levels, I first identify which rows correspond to the current group, then specify the population mean for that cell, and then generate a sample of random numbers. There are actually simpler ways to create the data for a one-way ANOVA, for example in exercise 5, but this construction generalizes to more complicated ANOVA designs that I'll show later. Finally, the data are entered into a data frame, and from here we can run an ANOVA and the visualizations as I showed earlier. So here we have Python code where I create a pandas data frame with the column group corresponding to the group column and the column value corresponding to the column data that I created in the last code cell, and then corresponding syntax in R. An advantage of creating code in this way is that you can manipulate the data characteristics of each level independently. For example, I did not specify a scale parameter, meaning that the variance for all cells is the same, sigma squared equals 1. This helps ensure that the assumptions of the ANOVA are met, but you could easily modify the code to violate the homogeneity of variance assumption or introduce outliers into one or all conditions. A parametric experiment. Here's an example of the kind of experiment that you can perform using this framework. I wanted to explore the impact of sample size on the p-value of the omnibus f-test when the population mean differences are small relative to the variance. So I created a dataset with 3 levels having population means of 0, 0.2, and 0.4, and a constant standard deviation of 1. This means that even the largest population condition difference is less than half the standard deviation. Then I varied the sample size from 10 to 150, stored the p-value of the f-test from each simulation, and plotted the p-value as a function of the sample size. The results show that with these parameters, even a sample size of 100 per group, so 300 subjects in total, is not guaranteed to produce a statistically significant effect. Of course, that conclusion changes quite a bit if the population means are further apart or if the data variances are smaller. This paragraph references figure 14.25. Figure 14.25 shows an experiment on simulated data showing the relationship between p-values, these are log transformed, and sample size in a one-way ANOVA. So we have a scatter plot with sample size on the x-axis ranging from around 10 to 150, and the y-axis shows log of the p-values ranging from -13 up to 0. There is a horizontal dashed line at around -3 approximately. This corresponds to a p-value of 0.05. Now what you see is that as the sample size increases, the number of dots, the number of p-values that are below that horizontal line is increasing. So there's a general trend downwards indicating more models had statistically significant effects. However, there were still many dots that were above the dashed line, indicating that even as the sample size grows, we are not guaranteed to get statistically significant results. This is remarkable considering that we know that the population means really do differ. That's how I simulated the data. Section 14.13.2, Simulation 2, One-Way Repeated Measures ANOVA. Next up is the one-way repeated measures ANOVA. Here, each subject gives multiple data values, and so we need an extra column in the data to identify which rows come from which subjects. You can see this in figure 14.26a, that each subject provides 3 data values, one for each of the levels. This paragraph references figure 14.26, which shows data simulating a one-way RM-ANOVA. In panel A on the left, we have a data table. Looks kind of similar to the one in a previous figure, except here we have 3 columns. The first column is subject, and the values in the rows of that column are 000, 111, 222. Then we have group, and the values there are 012, 012, 012. And then we have values, which are just randomly generated, normally distributed numbers. In panel B to the right, we have a box plot showing the distribution of the values in the three different groups. Back to the text. The new piece of code compared to the between subjects case is defining the subjects vector. That code is below, along with the group column, which is repeated from earlier. So here we have some lines of code. In Python, we have a group column that is using numpy.tile with the number of levels, so 0, 1, 2. That is exactly the same line of code that I described in a previous code block. The new line here is subject column, and here I'm using numpy.repeat, repeating for the number of levels the values from 0 to the sample size. And then there's two more lines of code for the corresponding R syntax. Back to the text. Notice the complementary nature of the code. The subjects column is a vector that counts up to the number of subjects repeated for the number of levels. In contrast, the group column is a vector that counts up to the number of levels, which is then repeated for the number of subjects. Interestingly, the data sets for between subjects and repeated measures contain exactly the same number of rows, so n equals 34 and 3 levels make 102 rows. But the between subjects dataset has a total sample size of 102, whereas the within subjects dataset has a total sample size of 34. The rest of the code to create the dataset is similar to the between subjects case. Modifying this code further to create a dataset with large individual differences is part of exercise 7. Section 14.13.3, Simulation 3, Two-way ANOVA. A long format dataset designed for a two-way ANOVA requires 3 columns, illustrated in figure 14.27a. That panel shows a dataset with n equals 3 subjects per cell, that is, per combination of factors a and b, and 3 levels in factor b. You can see the first 9 subjects from level 0 in factor a, then the levels in factor b repeat for a equals 1. This paragraph references figure 14.27, which shows data from a simulated two-way ANOVA. We have a table in the right in panel A that has 3 columns. The columns are labeled A, B, and Y. A is for levels of factor A, B is for levels of factor B, and Y is the dependent variable, which shows normally distributed numbers. Then in panel B on the right, we have the data visualized as box plots. Here we have a grouping of 2 groups on the x-axis for factor A, and then within each major group there are 4 separate boxes corresponding to 4 levels of factor B. Back to the text. There are 2 differences in the code to create the two-way versus the one-way ANOVA. One is that the means are listed as a matrix instead of a list. Now, technically, I'm still using a Python list data type, but the organization of the numbers is a matrix. These numbers encode the population means for the factorial design matrix. For example, the code below specifies a 2x4 ANOVA design. So here we have some code. In Python, its group means equals a list with 2 elements, and each of those elements is another list with 4 items. So the first list is 1, 1, 1.5, and 0.5, and the second list is 1, 1, 0.5, and 1.5. Then the next piece of code is the corresponding syntax in R. This matrix of means creates a crossover interaction with no main effects. Notice that the means of all columns and rows is 1. Figure 14.27b, which I already described, shows an example dataset generated from these population means. In a two-way ANOVA, you need to identify which data rows correspond to which combinations of levels from both factors. You can achieve this using the following code. Here we have a Python code block which has a double for loop we're looping over factor A and factor B, or I should say levels in factor A and levels in factor B. And then the row selection is a Boolean vector where column A equals little a, so the level in factor A, and column B equals little b. So basically the combination, the conjunctive Boolean for level in factor A and a particular level in factor B. Back to the text. There are a few other minor details that differ compared to the one-way simulations, which you can see in the online code and which you will explore and manipulate in the exercises. I used this code to run an experiment to evaluate the impact of population standard deviation on the p-values of the interaction term. The population means of factor B were 1, 1, 1.3, 0.7 for level 0 of factor A and 1, 1, 0.7, 1.3 for level 1 of factor A, thus producing a crossover interaction with no main effects and an n equals 30 in each cell. Figure 14.28a shows error bar plots of the data for one value of sigma. This paragraph references figure 14.28 panel A. That's the panel on the left, and here we see a grouped box plots similar to the one I described for the previous figure. Essentially, we have two groups on the x-axis for the two levels of factor A, and within each group we have 4 bars corresponding to the 4 different levels of factor B. Back to the text. I then varied the population standard deviation across all cells and stored the p-value of the main effect of factor B and the interaction between A and B. You can see the results in figure 14.28b. Not surprisingly, statistical significance of the interaction decreased with increasing standard deviation. The standard deviation parameter did not appreciably systematically affect the p-values of the main effect, although there were a few type 1 errors for larger values of sigma. This paragraph references figure 14.28b. This is the panel to the right of the figure illustrating some data. Here we have a scatter plot with the population standard deviation on the x-axis ranging from 0.1 to 2, and the y-axis is the log of the p-value ranging from -90 up to 0. As with the previous figure that also showed log p-values, there is a horizontal dashed line corresponding to p equals 0.05, so statistical significance. And then we have dark gray boxes and we have light gray circles. The light gray circles corresponding to the interaction term and the dark gray squares corresponding to the p-value of the main effect of factor B. Now the p-value for the main effect of factor B are almost all above the line with a few exceptions, whereas the p-values for the interaction term sharply decrease as the population standard deviation gets smaller to the left. So basically, the smaller the population standard deviation applied homogeneously across all cells in the ANOVA table in the dataset, the smaller the p-value of the interaction term. Section 14.13.4, Simulation for Two-Way Mixed Effects ANOVA. Finally, we have a two-way mixed effects ANOVA, which means one factor is between subjects and the other factor is within subjects. This dataset requires 4 columns: levels within factor A, levels within factor B, the dependent variable, which I labeled here Y, and a column to indicate the subject, here labeled ID. You can see from the data table in figure 14.29a that each individual provides a data value for all levels of factor B, but only one value for factor A. In this simulation, I set n equals 3, but why does the ID column go up to ID equals 3 in this snippet of data? Think of your answer before reading the next paragraph. This paragraph references figure 14.29a, which contains 2 panels. The panel on the left, panel A, is a data table. Here we have 4 columns for levels of factor A. Those are mostly zeros with 2 1s at the bottom. Factor B, and that's 0, 1, 2, 0, 1, 2, 0, 1, 2, and so on. Column for ID, for subject identifier. That is 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3. And then a final column for variable y, which is the dependent variable that's just randomly distributed numbers. And then to the right in panel B, we have the data visualized as box plots. There are 2 main groupings on the x-axis corresponding to the 2 levels of factor A, and 3 bars within each grouping corresponding to the 3 levels of factor B. Back to the text. The ID count exceeds n equals 3 because we have n equals 3 per level of factor A. With 2 levels of factor A, there are n equals 2 times 3 total subjects in our experiment. All subjects provide data for all levels of factor B, but only 3 subjects give data for each level of factor A. Of course, n equals 3 is a really small sample size, but this is just for illustration purposes. Section 14.13.5, A World of ANOVA Explorations. There are myriad ANOVA designs and parameters, and the exact setup of the design table depends on the nature of the experiment and the nature of the data. My goal here is not to provide an exhaustive list of all possible ANOVA scenarios, but instead to provide the tools and skills so that you can customize the code for your own explorations. Section 14.14, Non-parametric ANOVA alternatives. Non-parametric ANOVAs are designed to deal with severe violations of assumptions. Some ANOVA alternatives are based on comparing medians instead of means. Others rely on permutation testing to create empirical null hypothesis distributions instead of relying on assumptions of distribution shape. There are several non-parametric ANOVA variants. Here is a non-exhaustive list. Option 1, Kruskal-Wallis test. This is a non-parametric version of the one-way ANOVA, which can be seen as an extension of the Mann-Whitney U-test to more than 2 groups. It is based on comparing the medians of 3 or more independent groups. The Kruskal-Wallis test is implemented in scipy.stats with the function Kruskal and in R with the function Kruskal.test. Option 2, Friedman test. This is the non-parametric equivalent of a one-way repeated measures ANOVA and can be seen as an extension of the Wilcoxon signed rank test to more than 2 groups. It is implemented in Python with the function Friedman chi-square and in R with the function Friedman test. Option 3, Permutation ANOVA. This involves randomly permuting the data to create an empirical null hypothesis distribution against which you can compare your observed results. I do not cover permutation ANOVAs in detail, but you will learn how to create empirical null hypothesis distributions through random shuffling in Chapter 16. Option 4, Standard ANOVA after data transformation. This involves applying some transformation to the data and then applying a standard ANOVA. You need to be careful when interpreting the results if the data were non-linearly transformed. End of list. In general, non-parametric tests are less sensitive than parametric tests because transformations like rank remove potentially meaningful variability. If your data do not meet the assumptions of an ANOVA, it might be better to apply transformations or more stringent data cleaning than to apply a median-based ANOVA alternative. Section 14.15, Exercises. Please see my YouTube channel for video overviews of the exercises and my solutions. End of Chapter 14.